Can you hear me? Okay. Is the volume okay? Louder? This volume is good? It's good? Okay. So I'll keep this volume. Okay.
All right. Okay. Hello, everyone. This is the first session of the A Spotlight series. For you who are familiar, it's a discussion series with the speaker talking about their recent work. I'm very happy to have Hao Zhang from Google Research with us today. And we're starting briefly in neural text normalization, but give me a second so that I get the scene. All right, 1 second. Okay, all right. So yes, please go ahead. Hao, we're very excited to listen to your talk.
Thank you, Esel. Hello, everyone. My name is Hao Jiang. I'm from Google Research at New York. Our team works on speech and language algorithms. And this talk I'm going to present today is based on the journal publication, Neural Models of Text Normalization for Speech Recognition. And it's joint work with Richard Sprott, Axel Ng, Felix Stahlberg, Xiaochang Peng, Kyle Gorman, Brian Rock. So let me give an overview of this talk. So first, I will summarize the problem because the text normalization problem is not familiar with everyone. Next, I will spend most of the time on this section. I'll discuss the neural architectures that we propose in this work. And in the third part, I will discuss covering grammars to deal with unrecoverable errors that such neural models make. And finally, I'll present the results and give the conclusions. Okay, so what is text normalization? So text normalization, as the name indicates, it's about producing normalized text. So why do we need text normalization? It's actually a problem at the intersection of speech and the text processing. Let's just talk about one form of text normalization in this context, which is text-to-speech generation. So let's say we have a text in the left column, like here. A baby giraffe is 6 feet tall and weighs 150 pounds, but it's in the written domain. So you can see that 6 feet is not written as two words, 6 and feet, as the right column indicates. And so it's 150 lb. It's not written as the expanded form of 150 pounds, as in the right column. So the left column is called the written domain, and the right column has the spoken domain text. So the task is to translate the written domain text to the spoken domain. We have these special markers, self, to indicate that most words are actually just copies. They are identical between the written domain and the spoken domain. So we just need to copy itself to the spoken domain. We only need to do non-trivial transductions for certain abbreviations and the numeric entities. And for those, we call them semiotic class. That's the standard definition of such tokens. So there's another example. It's the more complex, like the date. It can you have to know that the number before the slash is the month, and the number in between is the day, and the last number is the year. So you have to know the convention. And the last token, $1.26, that can be read as actually $1.26. So you really need to expand it into very long form in the spoken domain. So why don't we treat text normalization as a machine translation problem, and why? What's the problem with this approach? So if we do that, it will be like translating the sentence in the first row to the sentence in the second row. And we can see that most words are identical between the two domains, and we only need to do interesting translations for certain tokens. So we just applied a standard transformer model to this problem. So how well does the model performs? So on English, the transformer model gives us a sentence accuracy of about 96.53. For Russian, the transformer model gives us about 93.35. So they're quite good. But keep in mind that the problem is has a very high baseline because most of the words are simply copied. If you just copy everything, you get around 90% sentence accuracy already. So the high accuracy is expected. So how well our approach should work? We actually can beat the transformer model, which is much deeper, much larger, and our models are consistently better for both languages. And we can say that the main drawback of end-to-end machine translation model is that it's hard to construct which output tokens correspond to which input tokens because it's taking the whole sentence as input and outputting another sentence. So it's hard to correct errors. But if it make a mistake on a certain numeric entity, you don't know whether it's coming from which region of the input it's coming from. So let's move to our proposed models. Our first proposed model is called sliding window context model. This is first proposed by Sprott and JT in 2016. In this journal paper, we rerun experiments for this baseline model, and on top of this basic model, we proposed more sophisticated models. But this is the backbone of all the variants we propose in this model. So it's actually based on the classic sequence-to-sequence model with attention. So the bottom represents the encoder layers. So the input is a region of the input sentence. Like the whole sentence is John lives at 123 King Avenue next to A&P. So this approach will take a sliding window around the tokens. So when we're trying to normalize 1, 2, 3, we will create a sliding window around 1, 2, 3 by placing two markers before and after the focus token. And we'll also take in some fixed window before and after the focus token. And that will be our input. And we'll take a character input as the input for the sequence-to-sequence model. And we run a bidirectional encoder to encode the input into hidden states. And then on top of that, we have a decoder network that goes from left to right to generate one word at a time. But similar to machine translation, we need to find the alignment between the output and the input. So that's where the attention mechanism appears. So what it works basically is at every RNN decoding step, the previous RNN state is used as a query into the encoder states at the bottom. And the alignment score is computed based on a neural network between the decoder state and each of the encoder states. And finally, every encoder state is given a weight based on the alignment score, and we produce a weighted combination as an input to the decoder RNN. So in that way, we can query the input dynamically while we generate the output. This is the only difference between the standard machine translation model and this sliding window model is we have a sliding window that moves along the tokens we want to normalize. So it's applied multiple times in each sentence around the interesting tokens that we want to normalize. There are issues with the sliding window model. First, it has a limited context. Like I said earlier, we use a fixed size window before and after the focus token. The second issue is it's it's doing repeated encoding computation because the sliding windows can overlap. So for every token in the input sentence, there can be a constant factor of window size n uh, repeated computation. And it also assumes the input is pre-segmented, so um, all the interesting semiotic classes have been presented. So we don't have to deal with identifying the regions to be normalized. That's assumed to be given. So these are all the limitations of the sliding window model, and they are all will be addressed in the following models.
Mm-hmm.
So this is the backbone of the new models we propose in this paper. In this paper, so the key difference is that we add a sentence context layer shared by all semiotic class segments in the input. So we avoid the repeated computation we mentioned earlier. Um, and the sentence context uh, is used by the decoder network in different ways. So the the arrows on the left and the arrows on the right indicates how they are fed to the decoder and network. So they are actually just in this picture. They are simply concatenated with the encoder states uh, produced by the attentional decoder.
Mm-hmm.
Um, or we can also choose other ways of utilizing the context. Like we can concatenate the context states and initialize the decoding RNN. So in that way, we only use it to give it a good context for the RNN to start decoding. We don't use it at every time step. But in this picture, we are using it at every time step. We give it constant hints that this is the context that we should do text normalization based on this context.
Mm-hmm. So how, a quick
Yeah.
clarification question on this slide. So I think it's pretty clear because of the indexing, but it
Hmm.
seems that your indices of HI minus one about the context layer I'm talking,
Hmm.
and HI plus one are also moving. So basically, as you're moving throughout your time steps,
Right.
you're querying the next items by LSTM or by that bidirectional GRU, I think you're using,
Yeah.
states as the next sort of context. And for the history context, you seem to be using H minus one,
Right.
again, both directions, hidden states. Is that correct? And
That's correct.
and in the middle, I'm trying to understand what that GRU doing in the middle. So
Mhm.
GRU mid. Were you going to go deeper into this, or could you?
Yeah. So the network in the middle is pretty much similar to the orange boxes at the bottom here.
Mhm,
Uh, it's encoding the input text we want to normalize. So in
mhm,
this case, we're only trying to normalize 1, 2, 3. So this GRU runs only on the digit sequence 1, 2, 3, and its context, unlike in the previous slides, it's represented as in a flat representation concatenated with the 3-digit 1, 2, 3. Here, it's represented structurally. There are uh, they are
mhm,
uh, first computed on the sentence level and then concatenated uh, with the orange box in this CIT context window.
mhm. So is it fair to say that I think what I'm trying to understand is, as a next question, this 1, 2, 3. How
Mhm.
is it detected? Like, is it? It doesn't seem to be so. If in a pipeline approach, not an end-to-end approach,
Yeah,
you
uh,
would have some
right.
NER.
I will,
Mhm.
yeah, I will talk about how to detect the region for normalization
Wonderful.
in the next few slides. Yeah, so in this slide, actually, we're still assuming that the segments are given, so we know where we need to normalize. So
Mhm.
this is a simple case where the 1, 2, 3 is a single word. It's easy to detect the segment, but there might be other cases where it covers multiple words. But we'll assume that the segments to be normalized is given, and we are we only care about the normalization task.
Gotcha. Thank you.
Mhm. Yeah. So, and we go deeper into the details of the context layer in this slide. So there are many different ways of representing the sentence context. You remember that in the previous slide, when we were talking about the sliding window approach, everything is represented as a character. So the basic unit is a character. But here we separate the sentence context from the uh, encoder layer for the region to be normalized. So we can use different representation units. Uh, for for text normalization encoding, you need to use characters because you don't want to miss any single character in the input. But for the context, the main task is to disambiguate, to choose the right class for the text to be normalized, whether it's address number or a, or a street number or a phone number, that kind of contextual information, class information is enough for context representation. So we choose the features in the context.
Mhm.
Um, so our choice is simply character n-grams. For each input word, we take unigrams, bigrams, and trigrams, uh, embed them and sum them up to represent every word. So that's how we represent the words in the input. By doing so, we don't have out of word vocabulary because the size of character unigrams, bigrams, trigrams is very limited for English at least. And this we find out is sufficient for context representation for the purpose of disambiguation. And it's efficient because the GRU length is uh, equal to the length of equal to the number of words in the input. It's not no longer equal to the number of characters in the input. If we use the number of characters input, it will be much longer.
Mhm.
So, uh, so now we talk about how we find the segments that we want to normalize. So that answers the earlier question about how do we get the uh, regions for normalization. So we actually just add one more layer, the tagging layer for detecting the regions to be normalized. So this is trained uh, as in a multitask framework as a new task. So this task will simply put a tag over each input word. Like in this case, we will tag the word John as self because it's going to be copied to the target domain, and we will tag the word 1, 2, 3 uh, as interesting, indicated by the character I here, because every word, because a segment can contain multiple words.
Mhm.
We also have to indicate whether this is the beginning of a segment or the middle of a segment. In this example, we don't have a middle of segment, but
Mhm.
we need to have that distinguishment. So we have to have another dimension in the tag set to indicate the position of the word in a segment. So that's why we have the character B here to
Mhm.
indicate the beginning. So that's the tag set. One, so this can be, once we have, if we have the training data, that the tag set can be induced from the segments given on the input sentence. So we can train the model to predict the text at the training time. At the decoding time, it works as we're given only the input words. We'll first try to predict the text set. Which will indicate the text set will indicate which words are to be copied and which words need to be normalized. So by doing that, we don't have to run text normalization, the more expensive attentional sequence or sequence model over every input segment. We only need to run that network over regions of interest. If a sentence has no interesting region to be normalized at all, everything will be tagged as self, and that's done. So it's only the tagging layer is run. There's no sequence-to-sequence model on top of it.
So can I just offer a very quick summarization on this slide, and maybe ask a quick question about it? So
Sure.
it seems that over here you add this pre network layer. This is also another GRU layer that's tasked with tagging which regions are of interest. And then if there are none, then the rest of the network will not be run. So you save a lot of computation. Okay, that's amazing. The part about your tags specifically. So I see in this image that you have a BI for 123, a BI for avenue. I don't see any middle or end tag. Are you just sufficing with just one, say, BI tag, and that would be the end of it, or you would actually have BM or BE?
I can. Yeah, actually, I have a BI and MI. You can even have a EI to indicate the end of the token, depending on
Sorry,
how,
yes.
how sophisticated the text set you want it to be. And it turns out that B and M is enough for our task. So we can, like in this example, because every interesting segment only has a single word, we don't have M. But a non-trivial example is like Jan 4th, 2019. So that will be a 3-word segment to be normalized, which will be normalized as January 4th, 2019 as a whole unit.
Wonderful. And then with your M's, so whenever your M's end, that's it. That's the end of it. So you don't have to explicitly mark the end of the region of interest.
Yeah. If it's after M, it's another self or another
BI.
Yeah, yes. That indicates it's the end of the segment.
Amazing. Thank you.
Okay, cool. So now we go to the first set of results we have, because we have presented the sliding window baseline, we have presented the context the sentence context models. We talked about how we represent the sentence context. So let's do a comparison of all these models. So we split the results into English and Russian, and the first row is sliding window baseline, and the following 3 rows are sentence context model with different representation units of the sentence context. Char means that the sentence context is also using character units, so it's much longer, but it's not lossy. It's taking all the input. It's not taking features from the input. And the next one is a word piece context. So it's chunking up the input into word pieces. Word pieces are used in Google's neural machine translation paper. In the original Google neural machine translation paper, they are just based on the frequencies of subword, how frequency a subword n-gram is, and accumulate that vocabulary and chunk up the input text.
Techniques such as byte pair coding, binary encoding.
Yeah. And the next one is the one I presented in the slides. That's the word feature context, where we take words as the input units, but we take features from the words and use bidirectional encoding over the word features. So they are sorted in the order of length. Character representation has the longest input length. Word piece is next to that, and the word feature has the shortest input length, because that's equal to the number of words in the input. But in terms of representation power, character is the most non-lossy. it takes all the information. If you have enough units, it should capture all the be able to capture all the input information. And the word feature is the most lossy. But we can see, at least for English, uh, uh, the word feature context works quite well. The star here represents it's a statistically significant. And in terms of speed, we can see that the word context, both word piece and word feature context are efficient. They speed up the sliding window approach by about 40%. Uh, and if we go to Russian, we can see similar picture for the speed up, but it seems like the contextual representation is more difficult in Russian, probably because of Russian is a morphological rich language. You need a longer context to disambiguate, to find the right logical reflection for the output.
Yeah.
So the character context get the best results because
Yes.
you can encode a very long distance and very detailed information from
Yeah.
the sentence context.
So in English, some it doesn't have it's as compared to other Romance languages or other languages in general, like Russians.
Yeah,
The morphology doesn't really tag a lot of, like, not too many agreements, right? We
yeah,
only have, for example, third person. But if there are longer dependency agreements, then if it's more challenging for you, and you
yeah,
need to capture
exactly.
that in the character. But a quick question over here. So it seems that this is my thought. Correct me if I'm wrong. It seems that with word peace,
Hmm.
it seems that it's possible not to lose, not to have any lossy transition. The reason for that is you can keep all your characters, right, and just
Hmm.
add subword information iteratively, right? So, so my understanding was that char and word peace are both non-lossy.
I see.
Is
The,
mhm.
I guess it depends on the vocabulary of the word piece model, right? If you use a large enough
Char
vocabulary
set?
size for your word piece model, then you can basically have no out of vocabulary words. But if the word piece, you choose a small vocabulary size for a word piece model, like say you only keep the top 1,000 word pieces, maybe there for rare words, there are still rare engrams that you can't cover.
So my understanding was that, and this is my assumption, I could be wrong,
Yeah.
that you can start with the bigger subword chunks,
Hmm.
and then if you don't have them, well, you can always go back to chars, right, for the word piece model,
Oh
and
yeah,
then
yeah,
if you
you're
have a
right.
complete
Yeah.
char set, then you would have a non-lossy, unless you don't want to use the complete char set.
Yes, yes, yes. You're right. You're right in that. Yeah. So yeah, I guess you're right that it's also non-lossy in terms of representation because it's not taking feature, it's taking the entire input. Yeah, yeah.
Yes. Yeah.
Thanks for correcting me. Yeah,
No, absolutely.
yeah.
This is really interesting to see. I'm interested to see how it unfolds. Please go ahead.
Mhm. All right. So let's move to the next slide. Earlier I talked about incorporating segmentation into the network, so we can do both segmentation and text normalization. So in this table, I will present the results of doing everything. So the results are still split between English and Russian, and for within each language, first we have the baseline word feature model with a pre-segmented input, and then the following two rows are the first row takes also trains the model using the multitask objective. It has an additional tagging loss. This is just to verify that adding a tagging loss is at least not going to hurt the main task of text normalization. And the next row shows that what happens if we integrate the segmentation layer into the inference pipeline. How does it impact the final accuracy, and how does it impact the speed? So the key story is that adding a tagging layer is really great for speed. Uh, the reason is, like I said earlier, if we can tokenize and predict what tokenize and also predict what classify the input as self versus non-self, we don't have to send that token to the sequence to sequence model to let the sequence to sequence model to predict whether it's self or not non-self. So that saves a lot of attentional decoding computation.
Mhm.
So that's how we get the speed up of almost 4 to 5 fold. uh, so that's great, and we can also see that we don't actually lose much in terms of sentence accuracy. Of course, we don't have perfect segmentation, but we can see that our segmentation prediction is really accuracy is really high. On the sentence level, we are at about around 99% accuracy in segmentation prediction. So that translates to very little loss in sentence, the final sentence translation accuracy.
How could you please clarify a little bit further what this segmentation loss is as compared to the other? Or basically, could you
Mhm.
quickly go over the rows? You have three rows: word feature plus tag loss and plus token tag.
Yes.
I want to understand the full picture, please.
Yeah. So the first one uh, is just using assuming the input is pre-segmented. So the
Yes.
task is only so the segmentation is 100% accurate.
Okay,
So
I
the
see.
input segmentation is golden.
Okay.
It's gold.
Hmm. Hmm.
So the task is only so the F score is about the normalization task.
Hmm.
So focusing on the tokens of interest and see what the F score is. Uh,
Hmm.
and the sentence accuracy is comparing the output sentence against the reference sentence. When they're identical,
Hmm.
uh, it's accurate. Otherwise, it's wrong.
Gotcha.
Um, so the baseline is just assuming the input the segmentation is given. The next one is also assuming the segmentation is given, but we train additional laws of predicting the segmentation and the classes. But
Hmm.
that law is not used. That's only used to kind of regularize the model, but it's not affecting the inference because at inference time, we're still using gold segmentation. We don't have to predict the segmentation.
Hmm. 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 Are
So
you
it's kind of
showing?
like a side task
Mhm.
that helps the model uh, in prediction, but it's not affecting the inference.
Very interesting. So you're saying you can still use the gold standard for inference time if it's available. If it's
Yes,
not available, obviously you can use
yeah,
the tag and
exactly.
network.
Yeah. That's the difference between the second and third row. In the second row,
Gotcha.
it's trained with a tagging like a segmentation or tagging loss, but it's at the inference time, it's assuming the input is gold segmentation.
Gotcha. So is the third row then, is it using, so it seems that the third row is not using the segmentation. Am I right?
Right. The third row is just using the raw input. It's predicting the segmentation
Predicting
through
the
a beam
segmentation.
search. Yeah.
Correct. And you have only a little bit of accuracy, like oh, it's an error decrease. So it's even doing better. Is that
No,
correct?
no, no. No, if we should look at the sentence uh, column, so
Hmm.
the error rate is in the parentheses. So
Gotcha.
yeah. So naturally it should increase because we don't have gold segmentation.
Sure.
So
Makes
that
sense.
arrow propagates to
Makes
the
sense.
final sentence accuracy.
Great.
But it's not too big. It's a worst if we this is for like productionizing the model is great because it gives us a great speed up and
Mhm.
actually does two things together.
At the same time. Amazing. We have
Yeah.
one online question apparently.
Hmm.
Okay. How so Masood is asking, can you elaborate on how you measure how you on your measurement of accuracy? Is
Uh,
our data set balanced, or in general, how does calculation of its accuracy work?
oh yeah, so the sentence accuracy is really simple. I mentioned earlier. So if the output is exactly the same as the reference, so all the words are the same, then it's one. If any of the word is not equal to the output, it's zero. So that's how the sentence accuracy is computed. Segmentation accuracy is ignoring the it's so the reference we just measure so this reference segmentation sequence is like self 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 beginning of an interesting continuation of interesting or something. It's a tag sequence. And
Mhm.
the uh, uh, hypothesis segmentation is another tag sequence. So only when the two tag sequences are identical, the segmentation
Mhm.
we count one, and otherwise we count it's a
Mhm.
zero. So
So the
that's how.
criteria is as hard as it can be.
Yeah, as hard as it can be, exactly.
Mhm. Beautiful. All right, please carry on.
And the data is so I didn't mention, but we can go to the paper about details how the data was created. It's basically a Wikipedia data set we already publicized. So it's draw from a similar distribution, same distribution as the training set.
Amazing. Interesting.
Okay. All right, so let's move on to the more more unique problem we have in this text normalization task, which we call unrecoverable errors. So I gave some examples. First one is 90 euro million, but it can sometimes be translated as $90 million. So the neural models we can make such mistakes, especially for these long tail uh, inputs, like the euro sign. It doesn't appear so frequent in the training data, but dollar sign appears very frequently. So the model has a tendency to favor the more fluent output according to the language model. So it chose to output $19 million versus 19 million euros. The second one, MA, that's also a rare unit in the input. So, but it's a red. It should be 3 milliampere amperes, but it's read as 3 million liters. So that's something. If you are only given the output, you're unable to recover the meaning. So
Mhm.
you're totally misled by the output. So that's why we call it unrecoverable errors.
Mhm.
Such mistakes actually also appear in uh, all the neural machine translation models. If you
Yes.
keep probing like any online translation service,
Mhm.
which are mostly neural network based these days, you will find similar errors for numeric entities or named entities. With yeah, so this is a common problem of neural models. They're good at head input, but they can make very bad mistakes on tail input.
That's very true. There,
Yeah.
I've noticed similar issues with other sequence-to-sequence neural sequence-to-sequence models,
Mhm.
including summarization.
Mm.
You
Yeah,
you may end up generating fake news
yeah,
unintentionally for the long
exactly.
tail events. That's very
Yeah,
true.
yeah.
Yeah.
So for our specific problem, we actually have a concrete solution, which we call covering grammars. So uh, it's a lightweight grammar which enumerates all the reasonable possible verbalizations for an input. Uh, it has a high recall, but doesn't care about the precision. The task of the RNN model is trying to choose the right output in the possible in the all possible reasonable verbalizations. So by constraining the output space, we avoid we guide the neural network towards reasonable output, so we can avoid catastrophic errors. Uh, but we can't remove all arrows. Um, so
Mhm.
let's go to more details of the covering grammar approach. This is based on earlier paper by Gorman and Sprott, 2016.
Mhm.
They reported a system that can induce a number name grammar as a finite state transducer. Um, so the problem is how do we read numbers? like how do we read the digit sequence 97 in French? It should be read as quad lan D7, but it's how do you create that grammar? One way, in the traditional way, is you let the linguists write grammars, and we can use some tools like in the FST library. There are grammar tools like the Thrax library for help that can help you create finite state transducers to produce the grammar. But in general, can we induce the grammar from data? So they answer this question. They can induce a finite state transducer grammar from around 300 carefully chosen examples. So the key idea is both the number name string sequence and the digit sequence can be mapped to the same semantic space with the arithmetic expression 4 times 20 plus 10 plus 7, because there are only still very limited ways humans express numbers. So you can enumerate all the given like a digit sequence, you can enumerate all the possible uh, uh, arithmetic expressions. And given a number name sequence, you can also enumerate all the possible arithmetic expressions. And if you take an intersection and on carefully chosen examples, it often, and you can land it on uh, a single agreed representation. So by doing that composition, you can induce a grammar that can map from number names to digit sequence.
Mhm.
And we take this approach and extend to more general semiotic classes. So let's say we try to induce a grammar, covering grammar for dates. So what we do is, which in the spoken domain, we have the spoken word sequence January 4th, 1999, and in the written domain we have Jan 4, comma 1999. And both can be mapped to the common semantic space with the string representation I show there. So we just need to come up with two FSTs to map to the common representation. And similarly, by choosing certain examples, we can intersect, we can compose the two grammars and create a written to spoken domain mapping grammar.
Wonderful. Just a quick maybe clarification for the audience. So for those of you who aren't familiar with finite set automata, finite set transducers, basically there are two categories. One category uses a deterministic approach, set up with a set of come up with a set of rules to transduce, well, translate your input sequence into another sequence that it appears for here to be a shared semantic space, right? And I understand that this is entirely deterministic. Is that correct?
Uh, it's it's entirely deterministic.
Beautiful.
Yes.
Okay. Okay. And because there's also probabilistic finite state automata that also can be used, but if the task can be tackled, adequately with a deterministic approach, then you don't even need to go that route.
Yeah, but there can be multiple outputs for the input, for the same input. So so take a example. If the input is 123, the output can be 123 or 123.
Correct.
Two possible outputs.
Correct. Very interesting.
Okay, so now let's talk about how we use the covering grammars in a sequence-to-sequence model. I'll only talk about how we use it in the decoding steps. So the decoding is like given the digit sequence 1 to 3, we have an output space uh, of the word sequences, and the FST gives us is a lattice. So it's given us the possible spoken word sequences represented compactly, like in this box. So what we do is while we are running the decoder RNN, we at every time step, we also maintain a state for the finite state transducer. So if we output the word 1, that's like consuming an arc of 1 in the finite state transducer. Then we move to the next state in the finite state transducer. So similarly, the RNN, once we output something, we move to the next state. So we are moving along both machines in the synchronous. And at any state, the FST will tell us what are the valid output arcs. And we from those from the list of valid output arcs, we can mask out the invalid outputs. In this case, only 2 and 20 are valid outcomes, so we can mask out the log gates corresponding to 9, 90, 0, and end of sentence, etc. So by doing so, we can constrain the search space by the lattice.
Beautiful. So thank you for the clarification. So I noticed that you did mention that it could be non-deterministic at steps. So for here, you see that the second step 20 and 2 is non-deterministic.
Yes.
Gotcha.
All right, so we have many tables reporting the results of covering grammars, but I took this table because it's based on manual analysis, but it showcases our results. We can compare. The best model is without covering grammar constraints in decoding, and the plus CG is adding covering grammar constraints in decoding. We can just focus on the Kaggle data sets because it's much larger and has more unrecoverable errors. We can see that clearly we reduce the number of unrecoverable errors by a lot in almost all categories. Yeah, so that's good. But the frequencies of such unrecoverable errors are very low. So if you just look at the final accuracies, you don't detect much change. So that's why we need such detailed analysis to. Also, it's difficult to automatically determine whether an error is unrecoverable or not. We need human intervention here to basic human analysis to pick examples that are to look at errors to see if it's unrecoverable or not. All right, so that concludes the work. So let me summarize the presentation. We present an efficient two-stage model for text normalization. The two-stage includes the tagging stage, which tags the interesting spans for normalization and the non-interesting spans for copying. And only the interesting spans are sent to the second stage to go through sequence-to-sequence transduction. And we focus on its application in speech, more specifically the text-to-speech case, where we're trying to verbalize written input, but it's suitable for other areas of text transduction as well, especially where the input and output are well aligned. You can induce token level alignment, so you can learn that tagging sequence more easily. One example is the reverse problem we call denormalization. Like it's used in speech recognition. In speech recognition, recognize spoken word sequences, but we want to render it into the written domain to give abbreviated forms sometimes. So that's the reverse problem. There, similarly, the model can be applied. And I can also think of an application in spelling correction, where most words are unchanged from input to output, but some words need to be changed according to the context. So you can also take a similar approach. You first tag which words should be copied and only do transduction on the words that need to be corrected. And it appears to be work better than heavyweight machinery such as the transformer. And because we have alignments in the output, it accommodates point fix mechanisms, like we can use a covering grammar or even a whitelist to cover certain input to correct errors. And we find that covering grammars are very effective in reducing unrecoverable errors, but covering grammars can be suitable for our problem because it's easy to induce such covering grammars for the task of text normalization. It's unclear whether the same approach can be applied to more general machine translation. And also it's an open research problem, whether we can completely eliminate certain types of unrecoverable errors. Like, can we remove all unrecoverable errors related to numbers in machine translation? All unrecoverable errors related to entity names in machine translations. These are very important for high quality machine translation. So there are many different alternative ways of attacking the problem. Like we can use data augmentation, use some synthetic data. We can also use active learning to use the humans in the loop.
Feedback.
Yeah. So there might be other ways of constraining the search space. So that these are all interesting directions of future work.
Great. Actually, one of them was my thoughts. If you can augment the corpus to have more explicit information for these long tail events, and then perhaps
Yeah.
your neural net could learn that as well. Very
Yeah.
interesting. Beautiful. Thank you. Thank you for the great talk so far. We seem to have a couple of online questions. If you would like to take some.
Sure, no problem.
Beautiful.
Okay. Um, um, Venkatesh asked earlier, I guess it's probably a question about data set as well. Has this method been tried in a case where you both have English and Latin in a sentence? For example, like the two character I dot E is what we use for writing, but when we speak, we say that is
Yeah,
English.
we do have we have a Roman numerals, so that I'm not sure that counts as Latin. Yeah, like like Elizabeth the second, like yeah.
Any other questions there?
Okay.
Okay, thank you. Okay, it appears that that was for the online questions. All right, very interesting. So which of, so we have 3 minutes until our sharp, cutoff. But let me ask you this: which direction are you most interested in going? So, because I see that, sorry, there's one more online question. Okay, we will have it. Maybe I ask this quickly, and then we go to the online question. Being a deep learning practitioner, I think I need to admit that I'm heavily biased into using end-to-end models. What is maybe just that's just a premise, but what is the next step that you're most interested in? Which
Yeah.
of these maybe future works or some other ones is the most interesting one that you want to work on?
Yeah, so actually the data augmentation direction is very interesting to me because it also includes a semi-supervised learning there. Like it's difficult to come up with spoken to written aligned data because there are not such a lot of such data existing uh, in the wild. So you have to manually create them. So if we can just leverage written only text or spoken only text and augment the training data, come up with some weekly semi-supervised learning method, that would be great. So for example, there are round trip translation ideas for machine translation for for semi-supervised machine translation. You can take English only corpus and try to translate it to French and translate it back. And hopefully you can improve both the English to French model and the French to English model by taking that monolingual data. Yeah, such models have some success, but so far we haven't seen very big improvements for our problem. Maybe our baseline is already really high, and adding covering grammar is helped even further. So adding data it will kind of unlabeled data it doesn't move the needle much, but it's still there are a lot of things that untouched fields in that direction. So I feel because that opens up alleviates the uh, training data problem.
Hmm. Hmm. Very interesting. Okay, one last question, and that would be it for today.
Okay. So Alice is asking, is there any difference using GRU versus LSTM?
On the GRU is only we only use it because it's cheaper than LSTM for computation. Well, we didn't find much difference in our final accuracy, so we don't go into details in the paper. But I believe for machine translation, LSTM usually works better.
Mhm. Well, it technically has more weights, right?
Yeah,
But if you want to, favor efficiency, the
yeah.
GRU would be the right choice. All right, amazing. It was really interesting listening to this. I'm thrilled to have gone through this together. Hao, thank you so much for your time and joining an ACE, the first ACE Spotlight event.
Thank you very much for the warm invitation, and thank you everyone.
Absolutely. Thanks very much. Have a great day.
You too.